appreciate, the invitation to come and chat with so many educators from across the province. I'm super excited here. I'm seeing in the chat, we have a lot of people introducing themselves and describing their relationship with mathematics. Anticipating some of the responses we're going to get, especially given the session that we are in, right? Where we're looking for, potentially some strategies or maybe some assistance in preparing for that test. And if you can see my screen, Jeff, everybody see that on the screen there? I've got one quote from the chat up from, I think it was, oh, now I forget. I cut the name off trying to be, a little more private here. But here, our friend from Woodbridge says that they have a curious relationship with math. They like exploring the subject creatively without any pressure to get it right, in quotes, which I love that, because what does that actually mean, right? It might mean something different to one person versus another, or memorize algorithms without really understanding what it means. And the reason why I spotlight this particular comment, I've seen a lot of others in there as well that I think are worth sharing. But when I look at this, I realize that I think a lot of people would probably agree in some way, shape, or form with this, whether you struggled with math or whether you felt confident, or I'm not even going to say confident, but you maybe didn't struggle. And the reason why I say that is because I was one of those students who didn't appear to struggle based on the grade I received, but I wasn't confident in mathematics. All right, there's a big difference there. And one of the big reasons why I think is about this idea of memorizing algorithms and steps and procedures without understanding. And that was me. I was just lucky enough that I could get through the system because I could memorize. And that gave me an advantage over so many of my peers. And that's really what we're trying to change in math education, is getting away from this memorization, or at least what I call blind memorization. Of course, we want as much to stick as possible, but we don't want it to be the opposite way, where it's like, memorize it and show me. We want to be doing mathematics, exploring mathematics, and the result of doing that work is that it sticks. And how we teach is going to really influence whether that happens successfully or not. So this one really resonated with me because, first off, exploring the subject. I don't remember it being very exploratory. I remembered it being this pressure to get it right, to get an answer. And like I had mentioned, I didn't really understand what it meant. But I also saw a couple others that I thought were really interesting. And this is, makes me feel very good when I see people like Courtney here, who says, I'm an older graduate who's rediscovering math and realizing it really excites them. And I'm hoping that that happens for everyone here at some point along your journey. It might not be today, but when you get to that place where you can see mathematics maybe as different than what you might remember it as a student. So now I've got another question for you, because I've got some tasks in mind that I think could be helpful. But what I want to know is, if you have like a certain topic or idea that is sort of like maybe making you nervous. Like I see Barbara said, I get nervous. But then when she researches it in order to teach it and she understands it, then she loves it. Like, think of this messaging and think about what we're going to hopefully do for students is we're going to hopefully help them understand it so that it isn't scary, so it doesn't make them nervous. So right now, are there any topics out there that people are thinking about and not feeling so good about? And then maybe we can start diving in to some ideas here. And I've got a couple in mind. Sometimes they, sometimes it doesn't come up, but one that I have in mind that I think could be really helpful. I see translations, fractions is common, linear relationships, exponents, mixed fractions.
Oh, how to.
Yeah, and I'm hearing some of our friends in there, even some of our friends thinking aloud, which is awesome. Word problems just in general. and anything grade 8 and 9. Interesting. So I've got a couple things, and actually I'm hoping I might be able to tie a few of these ideas together, and we'll see how far we can get here with some of these ideas, but keep them going in the chat. Of course, we're not going to be able to hit everything, but I've got a quick little prompt for you, and I want to fire this up on the screen for you to think about. There's the document camera. Let's get, let's see. Let's have a look here. I want to give, actually, you know what? You just gave me a great idea. We might be able to look at that one. I'll think on the trapezoid one and give you a good prompt for that in a moment. But I want to bring one up that I think a lot of people could benefit from, whether they realize it or not, because it connects to a lot of these ideas that we saw. Let's have a look here. What I'd like you to do is I'd like you to check out this short little animation, and it's going to be quick, and it's quick intentionally. I'm going to play it twice, and I just want you to notice and wonder, and you can do this right in the chat just as we go here. And then I want to ask you a couple prompts about what we see here, okay? So in the chat, anything and everything you notice and wonder, okay? So here we go. For example, you could notice a box or a basket. All right, so I'm seeing a few, we hear grouping, we hear volume with a question mark, like, is that what we're doing here? We definitely could. We could do a lot of things here. Keep them coming here. What are you thinking? What are you noticing? What are you wondering? Multiplication, capacity, rectangular prism, area. So much going on here. Awesome. Proportions, multiplication again, perimeter. Love it. Lots of great ideas. I'm going to do it one more time here. Just give you another look at this. Okay, here we go. And something interesting too is that I notice a lot of people are like trying to like name the concept or something. And that's actually not what I'm sort of pushing you for here. Just like, what do you notice? What do you wonder? Like, I noticed a lot of flowers. That was what I noticed. But open boxes, that's a good one. Awesome. Basket, empty baskets. How many flowers are there? Interesting. All right, we've got lots. There's flowers and baskets, all kinds of stuff going on here. And that's where I'm going to lead you here. I want you to make an estimate. I want you to think about how many flowers do you think you saw in that final frame based on what you saw. Now, before you share, some of you may have already hit enter, and that's okay if you did, but before you share your estimate, I want you to pause for a second. And I want you to try to think of what you remember in your mind, maybe about that first frame, and then also about how many you think you saw on the screen. And most importantly, before you share your number of flowers that you saw, I want you to think about how would you explain that number to someone? Like, what would be your reasoning? What would be your logic? All right, I'm going to give you about 20 seconds to think this through. It's only an estimate, so there is no right answer here, all right? And there's no judgment, of course. And then when I tell you to go, I want you to share just the number of flowers, and then I'm hoping that a few people will put their hand up and are willing to share their thinking of how many they may have seen. All right, so I'm seeing numbers are coming in. If you haven't yet, hit that enter button and let us know, how many do you think you see? All right. Now, Jeff, I'm wondering if you're willing, can you help me with some of the maybe lower numbers that you saw? Like, what are some lower numbers that you saw?
40, 25.
25. You saw
54.
40. Oh, 54.
There are a few of those.
Interesting. Keep going. Give me some more now. Maybe some more near the middle or near the higher end. What did you see?
72s and 78s.
72s and 78s. I'll throw those down here.
And I've seen as high as 180 and 126.
Okay, so 180 is like over here. Did you say 126 you saw?
Yes, 126.
126. I'm going to fire that somewhere around here. Okay, so we've got a pretty big range over here. All right, so that's our first set of estimates. What I'm going to do right now is I'm going to share that image one more time, and I want you to update your estimate in the chat as soon as you're ready to, okay? I want you to update that estimate. You might want to think on it a little bit first before you share. And this time though, I'm going to make sure that it's pretty quick that we move away here. All right, so we are now updating our estimate. Most importantly, I want you thinking about how did you come to that conclusion? And then we want to unpack some ideas here, some thinking. Oh, we're seeing some 72s, more 72s. It seems like we're getting closer to this range here. And oh, lots of 72s, like lots of people coming in on 72. I'm wondering, is anyone brave enough to raise a digital hand and give me an idea of what you were thinking? Like, how did you know and how did you do it? Like I see Joy did it in the chat. So I'll wait for some hands and I'll just read what Joy said. Joy said, I counted 12 boxes and 6 flowers in each box. And I actually saw a lot of people do that. There were 12 groups of 6 flowers. And I'm wondering, how could you do 12 times 6 if you don't know what 12 times 6 is though? Like what might be a strategy I can use in order to figure that out? Because like I'm not good with like my 12 times tables. I don't know. Oh, interesting. Juana says 10 times 6 and then 2 times 6. So what I'm hearing you say is like, you're like, why don't I break down my 12 into 10 plus 2? And you're telling me that basically I want that to all be multiplied by 6. And when you say 10 times 6 plus 2 times 6, what you're really using is you're using this thing called the distributive property, which is super helpful with multiplication. So it's like, I can do this and kids can do this a lot easier than when we write it symbolically. Like in school, I memorized this. It was like, when there's a bracket, this number has to multiply by this number and this number has to multiply by that number. That's what I remember doing. But like my daughter can go, well, 12 is 10 and 2. So she goes 10, 20, 30, 40, 50, 60. And then she goes 2, 4, 6, 8, 10, 12. 60 plus 12 is 72. And boom, she's got her answer of 72 flowers. Super cool. Awesome stuff. That's one strategy. Did anyone think of it differently? Wondering if there was anyone else who thought of it differently. Any other ideas out there? Interesting. And if I actually bring this up, I just want to highlight here before we, oh, look at that. 4 columns and 3 rows with 6 in each. Like what I'm envisioning in my mind is like, you've got, you said 4 columns and 3 rows. So it was like, I had all these flowers and I had 4 columns and 3 rows. It's like I've got this array, multiplication array, which is great. And you knew that basically in each one you had 6 flowers. So I could do this a number of ways. I could be like 6 plus 6 plus 6 plus 6 and do that repeatedly. I could do 5 plus 1 plus 5 plus 1 plus 5 plus 1 plus whatever I want to do is great. Or I could break this down in any other number of ways that I'd like. So you've got this array. So you could have went and said, well, I know that there's actually, 12 groups of 6 like we saw. Or I could have broken it down in any other way I'd like. Like if this is 6 and this is 6, then wait a second, then this is 10. I can like see 10s. Like, oh my gosh, there's 10, there's another 10, there's another 10. got 2 left. There's 6, 6, 8, 10. Here's another 10 right here. Here's another 10. So there's all kinds of ways that we can solve this, and then I can worry about the leftovers over here. I've got 4, 8, 12. Look at that, 60 plus 12 is 72. I've got all kinds of ways that I can work through this problem. Super cool. Okay, that was just a warm-up problem though, okay? Because my real question is this. What I want to do is I want to take these 72 flowers that I shared with you, right? Here they are. Like I've got 6, 12, 18. I can maybe double that, double it again. There's our 72 flowers. Except this time, what I want you to do without a calculator, and I want you to be thinking here for a second, if I have 72 flowers and now I have got only 4 larger boxes to distribute these flowers to, my question is, how many flowers would I get per box? And how do you know? So that is what I'm really wondering here. I'm going to give you a little bit of time. If you want to share it, you can obviously put your hand up and then we can put the spotlight on your camera to share. But right now, what I'm going to encourage you to do is not to, and I know I should have put this and prefaced this earlier, but it's not a race to get the number. I'm actually less concerned about the number. So go back to that quote we saw at the beginning. It's not about getting the right answer here. I'm more curious about how did you do it? And I'm curious what it relates to, like what have we done mathematically? And then I'm hoping we can make a couple connections here that relate to some of our challenges we saw in the chat. All right, we're seeing some answers coming in, which is awesome. Valentina says they visualized undoing it, which I think is pretty cool. Super cool. Sandra's saying they divided. And then what I'm really interested in is like, how could you articulate it to someone else? How could you, communicate that? And I'm going to look for some hands. I don't see any up, but if anyone's willing to share, turn a mic on and share, that would be fantastic, because it does get lonely. I'm sure, Jeff, you must feel that way sometimes, eh? It's a little lonely.
I agree.
He's like, yes, it does. Absolutely. All right, let's see. I see one hand up. I just can't see whose it is. Oh, there it is. Is it Sama or Sama? Go ahead and let me know how we pronounce your name correctly.
My name is Sama.
Sama, awesome. What are you thinking? Like, how would you help to communicate your thinking about these 72 flowers in 4 boxes?
I will distribute an equal number in each box.
Interesting. So if I have 72 flowers,
I divide them by 4, then I distribute them in 4 boxes.
Okay, so you're saying like divide. Now my question is, I like how you're saying distribute them, like, but now how would you do that? Like, how are you doing? Is it a known fact in your mind? You're like, I just know 72 divided by 4, or how would you convince someone who doesn't have that fact?
I'll divide 7 by 4 first.
Oh, interesting. So how would I model that for someone? Like, what would that look like?
You can do long division.
Oh, long division. Okay, cool. Let's do it. So I've got, okay. So what do I do for long division? And we'll come back to see how this, maybe we can visualize what's going on here.
I will say how many 4 goes into 7.
How many 4 goes into 7, which is 1? Awesome.
And 1 times 4, it's 4. Then 7 minus 4 is 3. Then bring down the 2. Then I divide 32 by 4.
Awesome.
Which is 8. 8 times 4 is 32. And that means I have to put 18 flowers in each box.
Super cool. So there's long division, which is interesting. And we'll come back to that in a second. Interesting. Did anyone have, and thank you for sharing, by the way. How about Marina? What was your thinking? Like, how did you go about this?
I thought I will go up to 80 and I will divide that by 4 and take away 8 out from it.
Super cool. So what you're saying is it's almost like you're like, well, let's pretend we have, is it 80 flowers?
Yes.
Super cool. You're like, I got 80 flowers instead. And you're like, I'm going to divide that by 4 boxes.
20.
And that is 20 per box.
Mm-hmm.
Interesting. And then how did you know what to do to adjust this?
I will take away 8 of them out because it's 72.
Super cool. So it's like you went from 72, you added 8. So now somehow I need to get rid of 8.
Mm-hmm.
Okay, so why not just like subtract 8 from the answer? Like what's going on there? What do you think? Any thoughts, anyone? And feel free, Marina, if you want to help us with this. So is it like, is the answer now 12 per box? And I'm going to go ahead and draw out our 4 boxes for a second. And I want to take my 80 flowers. And if I was to put in like, I'm going to use 10 rods to kind of represent this. It's like 10, 20, 30, 40, 50, 60, 70, 80. So there's my 10 rods that I've used. I've got 80 in there, but the problem is I didn't have 80. I got to get rid of, I need 8 to remove. Why can't I just take away 8 from my answer of 20? You can see that 2 10 rods is equal to 20 there. What are we thinking? Any thoughts? I see Marina still has a hand up. If you do and you want to share, feel free to just turn the mic on. What are you thinking? I'm ignoring the chat. Sorry, let me look. What do I see? Azra says it's 20 per box. So I can't take away 8. Otherwise, if I take away 8, then I'd be removing 8 from this box, 8 from that box, 8 from this box, 8 from that box. So in a way, it's like, wait a second. It's like I have to remove 8, but I have to remove 8 total. If I divide that by 4 boxes.
Yeah, then you can take it 2 in each.
Then I'm going to remove 2 per box. So if I get rid of 2, get rid of 2, get rid of 2, get rid of 2, I'm going to end up with my 18. I'd have to break up my 10 rods in order to get my 18. Super cool. Love that. Love that thinking. All right. Now I want to share something with you because what we have over here is we've heard that a lot of people used division. One thing I want to go to is this right over here, which is the algorithm. And I want to share what's really going on in this algorithm for a second. First off, this division, you'll notice that we fair shared our flowers. So we've basically taken our 72 flowers and we could fair share them to the 4 boxes. However we choose, we can go 1, 1, 1, 1, then another 1, 1, 1, 1. And I just keep counting over and over. And when I run out, I run out. Or we can do 80 flowers. We can add 10s to each. We can do all kinds of things. But something I want to share with you, and it's kind of related to this long division model over here. It works. It always works. But there's a few things for us to maybe consider. And if we think about this for a second, is that what we've got is essentially we're looking at 72. We want to get 72 flowers and we want 4 per, we want 4 boxes. And what we're trying to do, so if these are my boxes, and if you were to think about that for a second, so here's like 1 box, 2 boxes. So these are like my boxes. They're very long boxes. And I'm trying to think of like, how do I get 72 in total? What a lot of students will start doing is they'll say, well, let's start figuring out how many flowers we need to do here. So what they tend to do is they use 5s and 10s a lot. They go, well, let's pretend there's like 10 flowers per box. And when they do, they go, wait a second, 10 flowers per box. That means there's 10 in the first box, 10 in the second box, 10 in the third box, 10 in the fourth box. 10 times 4 is 40. Oh my gosh. So there are 40 flowers right there. And then they start working their way and they go, okay, well, I've got 40 flowers. If I do this again, if I go another 10, I'm going to be at 80 flowers. I can do that and work my way back. But what students will often do is they'll say, well, maybe if I go with like 5 flowers per box, okay, I got 5, 10, 15, 20. Okay, let's have a look at that. So now I've got 20 flowers per box. Notice in total, I have 60 flowers taken care of here. I still need to get to 72. I need 12 more flowers. Some students might realize, oh, wait, 4 times 3. If I had 3 more flowers, I'm going to get my extra 12, and we're at 72 in total. And I want to pause for a second because something that happens in long division is you get forced, you're doing the same work as this model over here. This is an area model, except you're forced to pick the biggest number that can fit. You said, I heard 4 goes into 7. It's actually, how many times does 4 go into 70? And we go, well, it goes in 10 times perfectly. That's where that 1 comes from. 10 times 4 is 40. There's actually a 0 there. So this 40 is the same as that 40 right there. Okay. Now, what is hard for a lot of students, including maybe some of us in this room right now, is this idea that it's like, okay, well, now I have 32 left over. Well, look over here. We had 32 left that I needed to take care of. And what long division forces us to do is to pick the highest factor that's going to work. So it was 8. Whereas notice how here we got to split up that 8. We got to be more in control. Now I can do that with division all I want as well. I just have to keep track of what I'm doing. So for example, I could go like this, and instead of following the long division rule, I could just say, well, I know that, let's see, 10 times 4 is 40. Okay, well, that takes care of that. That gives me 32 left. And then I go, okay, well, 5 times 4 is 20. Okay, I'm going to put 20 there. That leaves me with 12. And I go, oh, wait a second, 3 times 4 is 12. And I know that I'm in good shape. If I add it all up, 40, 60, 72, and then I've got my answer right here, 10, 5, 3, 18, and I'm in the same boat. And now it looks identical to what we've done in this model over here. For me, this model helps me keep track of what's going on with the numbers a whole lot more than going over here. So if you're like me, and I'm curious in the chat, I want to get a response from you friends. How many people memorized long division? And be honest, how many people had to re-memorize long division to prepare for this test that's coming up without necessarily understanding it? Let me know how you feel about long division. Have you always like felt good about it, or has it just been something you didn't really understand? I know for me, by the time I got to high school, I forgot how to use long division because it actually isn't that intuitive. Courtney's saying it came back easily. Interesting. Yeah, like, I mean, times tables for some people, they're like burned in your mind, not a bad thing, right? But we need to know what it means, right? So for long division, it's a tool, it works, but if you get stuck somewhere along the way, sometimes it becomes pretty hard. So I guess what we're saying here is just be cautious. If you're out there and you're like, I'm not really feeling good about long division, keep in mind, we can draw this out and we can take our factors and essentially just work our way and figure out, what do I need to find here? Now, super cool. Okay, so let's have a look at this for a second because we have an answer. I think we'd all agree it's 18 flowers per box. Now, I just want to introduce you to a model that will be helpful to you, because what if I was to share something here? I'm going to share something with you, and let me just bring it up like this for a second so we can see our 72 flowers in 4 boxes. I just want to represent this in a linear fashion for a second, because this is going to help you with a few ideas, I hope, today. All right, I'm going to let this bar represent 2 things. I'm going to let it represent our flowers. Okay. And we said we had, with 72 flowers, we had 4 boxes. And my question to you is there a way that we might be able to get close to this answer by using this model? I want you to pause, maybe notice and wonder for a second. If this is 72 flowers and this is 0 flowers, and if this is 4 boxes, because these are going to go into that, and this is 0 boxes, my wonder is, like, I don't know, can anybody help me understand, like, whereabouts would you put 2 boxes? Where would you put 2 boxes? What do you think? I'm curious about this. In the middle, we hear. Awesome. I'm going to go ahead and assume by in the middle, you mean like right, chop, right there. No, right there, right about there. Okay, I'm going to chop that. I'm just going to put that down for a second. This isn't for you. This is more for me. I like seeing it a little bit here. So, okay, I got 2 boxes. I'm curious though. Okay, so I had 4 boxes, 72 flowers. We can see them basically right. If I was to share this with you, where are they? I can't see them. Where are they? There they are. There they are. Boom, there they are. Now, if you kind of envision this a little bit, it's almost like we're stretching these boxes out a little bit. I'm curious, if I was to take my 72 flowers and I had 4 boxes, but then I was to take 2 of the boxes and like give them away, I'm wondering, how many flowers would I have if I only have these 2 boxes full left over? How many flowers would I have? Ooh, Courtney's saying 36. I'm curious, how do I know that to be true? Help me understand what's actually going on here. Anybody help me with that? Like, what did you do to get from like what we know to what we now know? Half of 70, I love the language. So you've actually, when you say half, what you're telling me is you've actually used multiplicative thinking. You've taken 4 and you've halved 4. Half of 4, okay, so I'm going to write it over here, like half of 4 is 2. 1/2 of 4 is 2. And that feels intuitive, okay? And the reason I'm writing this, because I want you to realize you're multiplying by a fraction when you're halving something, okay? You're multiplying by a half. Super cool. And the same's true over here. You folks said, well, like, I took like 1/2 of 72 flowers, and that gave me 36 flowers. That's pretty cool. Awesome. I'm wondering, I'm wondering how many flowers per 1 box, and we already know the answer, I know, but where does it go? Help me understand where it goes. And then I want to share something with you that you have done that you don't realize you've done. Crazy. half of 2 and 36. So I'm assuming you mean like half of 2 and half of 36. So what I'm gonna do here is like I'm having again, and I'm having again. Okay. So we're using like multiplicative thinking here. I'm gonna say it's probably somewhere right around here. And we know it was 18. We're feeling pretty good about that. I love it. My question to you is this. Where does 5 boxes of flowers go, and how many flowers are in 5 boxes? I'm going to give you a little bit of time to think on that. And then I want to really unpack what we just did and what it really was, because you folks told me that it was just division, but I'm going to argue it's like more than division. There's like a lot going on that we don't realize is going on right now. And I hope it's going to help you with some of your adventures on this, this test. So I'm going to give you a little bit of time, a little bit of think time. I want you to actually draw it if you haven't already. Like where does, and I'm going to write it down. Like, so where does 5 boxes go? And how many flowers? Now, if you feel good about it, like maybe you haven't drawn it out yet, but like you're feeling like you know where it goes, I want you to throw a hand up. I won't necessarily pick you. I'm going to give you an opportunity to put your hand down if you do not want to be selected. But I'm just curious to see how many are feeling good. Feeling good. All right, I'm seeing some people are saying like it's going to go like after 72. I would agree, like 5 boxes is going to go after 72. I think this marker is done. It has experienced too much virtual learning this year in my document camera. Okay. Now, who is brave enough? I don't see any hands. So either you're sleeping, you're out in the backyard and you're like, I'm pretending I'm there, but I'm giving up on this guy. That's cool if you are, by the way, no judgment. But I'm wondering, is anyone brave enough to just turn on their mic and try to describe to me, where am I going to put it? Because like, I agree it's going to go over here, but like, how can I like feel good about that? How can I like feel like it goes around a certain spot? What can I use as a reference point, and how many flowers?
I don't mind saying something about it.
You're the best, whoever's talking. Who is that?
Joanna.
Joanna, hello. Thank you.
Hello. I'm doing great. So basically, I looked at how many we had with 1. We had 18 flowers in 1 box. So if we notice that we have 4 boxes, we're only going up 1 box. So that means that we're going to add 18 to 72.
Super cool.
That is going to be 90. So it's going to be just a little up to the right beside 4.
I love it. Now, what if I was like, and this is more what I do with students, but I'm going to do it with you friends too. Like, how can I be precise? Because like I could put it there, but I don't know. Do you feel good about that?
No.
How would you know about, like, what could you use as reference point to help me along here?
You can look at the distance from 0 to 1.
Oh, super cool. So if I was to take like, I don't know, maybe like a little paper strip, you can tell I do math a lot. I got little paper strips around and stuff. Okay, so here we go. So I think what you're saying is like, it's going to be like that much further. So if I kind of do that, I feel pretty good. It doesn't have to be exact. Here we go. Let's get that cap off there. It's going to be like somewhere maybe around here, I'm thinking. You feel good about that?
Exactly.
Super cool. So you told me it's like, okay, we're going to go up 1 box, and we're going to go up 18 flowers, you said, and you said that was 90 flowers, and this is 5 boxes. Now, I'm going to pause here for a second. Notice something interesting that's going on here, that sometimes we confuse, us humans confuse, when we don't have a model to work with. it's hard for us, or I shouldn't say hard, it's easy for us to make silly errors because we're kind of working in an abstract place and there's really nothing to like ground ourselves in. But notice here it was like I halved. Like here, I didn't just go like +1 or plus 18. It's like I'm now thinking additively, which is very different than thinking multiplicatively. So what we actually have here in this problem that we thought was just division is actually a lot of proportional reasoning going on here. And I'm going to argue that even though I didn't initially ask you this question, had I originally asked how many flowers in, oh gosh, all my markers are going away, in 5 boxes, many of you would have felt like, this is now a tough word problem. But in reality, what I knew was that I had 72 flowers and 4 boxes. And what I needed to figure out was how many flowers are in 90. And this is typically how we were taught in school and how I taught my students for a long time before I realized what was going on, is that actually what I have here are ratios. And they're all equivalent ratios from the same proportional relationship. Is anyone brave enough to identify for me one of the ratios in this proportional relationship? Anyone want to be brave? You can do it in the chat if you don't want to just turn your mic on. Casey says 1 to 18. How many people feel good about 1 to 18 as being a ratio in this proportional relationship? I saw a hand. I see a couple other hands. Anybody have any others? Because remember, it's a relationship. So did you know that every ratio has an infinite number of equivalent ratios? Like, think about that for a second. Look, 4 to 72, someone said, 4 to 72. Oh gosh, what else? 2 to 36. Did we even do that one? Yeah, we did that one. I'm going to argue that there's 3 to a number there. There's 4 to the number there. There's 5 to 90 we saw. There's all kinds. There's half to, anyone dare? Half a box to how many flowers and a half? Oh, I see 3 to 54. I love it. How about half? Half a box of flowers, half to 9. So you notice, like, it's not formal. We usually don't see a lot of ratios that have fractions in them, but you can write them that way. Like, be a daredevil, be crazy, like do whatever you want. But really, this problem, if we didn't already solve the division per 1 box over here, the problem I actually was asking right here was this one. I said, well, there's 72 flowers in 4 boxes, and that is equivalent to some number of flowers in 5 boxes. That is the exact same thing as what we just did here. Do you see it? Look at this was X. This is an equivalent set of ratios, 2 equivalent fractions. This proportion is just taking this huge diagram of all kinds. Like, if you think about it, every single ratio is here. It's just not marked, right? Like, if I stop the pen, there are 2 numbers here, boxes and flowers, that I can put. Same here, same there, same there, same there, same there. Some of them are going to be fractions, right? They're not going to always work out perfect, but there's a number that goes there. We're just not showing them all. Just like on a ruler, when you see 1 centimeter, 2 centimeters, 3 centimeters, there's everything in between. We just don't mark it down. So if you picture, every proportional relationship can be modeled using what we call, like here, this is like a tape diagram. Think about a measuring tape. It's like same idea, a tape diagram. We're showing the relationship. And when you actually use a tape diagram or a measuring tape and you roll it out and you see centimeters on the top and meters on the bottom, you're just showing equivalent ratios of 100 to 1, right? Every 100 centimeters, 1 meter. 3 meters, 300 centimeters. It's just a bunch of these proportions that are going on here. And there's a few things that are really interesting. This right here, this one is a really important ratio that actually makes it really easy when we divide. Like, look at this, 72 divided by 4. I sort of wish I flipped it a little bit just because now it's going backwards a little. But let me just rewrite this for a second. I'm going to go 18, whoops, to 1. I'm going to put 4 to 72. I'm going to put 5 to 90. Something really cool about the ratio colon that we're using here, that we commonly use, is that actually in some other countries, they actually use this same notation as the division sign. Notice how the division sign looks awfully similar to a ratio. It just has a line in between. That's kind of cool. I wish somebody told me that, because look at this. When I go 18 divided by 1, I get 18 flowers per box. Oops, I did it. Shoot, I recopied it the same way. Goodness me, what is going on? It's been a long day, you can tell. Okay, I had 72 and 4. I had 18 and 1. I had 90 and 5. So over here we have 18. When I divide these two numbers, I had 18. When I divide these numbers, I have 18. And you know what all of these numbers are when we say flowers per box? Can anyone identify what this is called right here? I got all these ratios. When I divide them, I get the same answer in this proportional relationship. Anybody have a name for it? I'm seeing common denominator. Like a common denominator would be this idea that, you know, if I was to write them this way, for example, like 18 over 1 and 72 over 4, these aren't common denominators, but there's something going on there. Someone's saying linear, constant. There's a magic word. And the one that really identifies it, what's that, sorry?
Maybe factor.
Ooh, interesting. A factor. It could be used as a factor, absolutely, like a one of the two factors in a multiplication problem. This is the key word for me that really helps me identify what this is. This is my rate. Over here we have ratios, and right here we have a rate. And you'll notice that all of these equivalent ratios yield the same equivalent rate. And a rate is how much per one of something. That is the rate. Now, a lot of people say, well, isn't 18 to 1 the rate? And I'm going to argue, no, not yet, because we haven't divided yet. We haven't divided this into my 18, because now my answer is 18. My answer is 18, 18, 18 what? 18 flowers per box. Just like when you say, I went 400 kilometers in 4 hours, that's a ratio. But when you divide that, you get 100 kilometers per hour. And that is a rate. Is that cool? Pretty interesting stuff. Now, something that I'm going to pause there, and I'm curious if there's any wonders, questions, or confusion, because I tend to like ramble on a little bit, especially when we're only together like this one time. It's like I feel like you're like my class that I'm meeting for the first time on September 1st, but it's also June 30th, all in 1.5 hours. That to me is really heartbreaking. You know, it's like we're just getting to know each other, and then all of a sudden the school year's done. You're all gone. So I'm wondering, any thoughts on that? Any questions or wonders? All right, I am going to do something here because I think it is definitely worth exploring. I heard some people saying like linear relations. Now, I used a word over here somewhere, proportional relationships. Okay, so we're going to start there, and then we're going to kind of nudge our way to a linear relationship. And I'm going to argue proportional relationship is a subset of a linear relationship. Okay, it is a linear relationship. It's like one of the linear relationships that are possible. It happens to be one that we explore in everyday life all the time, especially through this idea we just explored today, is this fair sharing idea. Like, would you all agree? I think the very first strategy we saw or heard today was this idea of fair sharing, right? They're like, take the 72 flowers and share them amongst 4 boxes. That's because we were giving you flowers and boxes, and it's like kids and cookies, right? Cookies, 4 kids, they each get 18, and we do that through fair sharing. So this is a proportional relationship, and it all begins with multiplication and division, and it's super, super important in order to get to more complex thinking like linear relationships and other relationships that come later on. But first thing I want to do is I just want to take our tape diagram, and if you didn't see it, or if you didn't realize explicitly, like I could literally take this tape diagram, and do you see how if I go like this, it turns into a table of values? Like, I'm going to put it like right, I don't know, like right, should I do it right there? No, I'm going to do it over there, and I'm going to let it just sort of sit on the edge for a second. I'm just going to rewrite it as like, I don't know, more of like a formal table. Like you might have seen it like this in school. You'd be like, okay, well, I got boxes and I got flowers. Is that cool? And like, notice, like I already got them. Like I'm kind of wasting your time and my time, but you told me that like 0 boxes, 0 flowers. You also told me 4 boxes, 72 flowers. Some of you said, well, you know, you knew where like 2 boxes and 36 flowers goes. The only difference here is like here we're using scale. Like see how we cared about how far it was? In a table, we don't really care, but I tend to pretend to care, you know, if you know what I mean? Because like, I kind of like to still have that idea. So I kind of put it halfway. Like here's my 1 and my 18. And from here, I can unlock this entire proportional relationship. Now, what I want to ask you specifically as I look here, I'm also going to put our 5 and 90. I'm wondering, like, what if we wanted to know how many flowers, like we're talking big time now, we're doing a wedding and I need a lot of flowers. If I told you, like, I actually wanted like 101 boxes, like, how would you figure out how many flowers? Like, now that we've sort of unlocked this problem, how might I do that? And then I'm wondering what this might look like if we could like figure out, is there like an equation we might be able to come up with? Is there like a rule or something? I feel like there's like a pattern going on here of some type.
Can I talk?
You sure can.
Yeah.
You turned your mic on, so of course you can. What's your, is it Anella?
No, that's me, Janet. I just used my daughter laptop, so that's
Oh, well, you know what? Hey, now you're hacking into her account. I love it.
Yeah, because my other laptop, I don't know, it's not working. There's a problem.
Yeah, no sweat. What are you thinking?
I think we have to do the ratio. Like if we say like 1/18, and we other side equal 101 over x.
Okay. So you said 1/18 and 101 over x. Now, I'm going to tell you that you definitely can do this. This is, you can totally do that.
Right?
You could totally, I personally, I never use cross multiply. I used to teach my kids to. And the only reason why is because if I asked you why it works, most people are like, I don't know, it just works. So what I'm going to encourage you, like, let's pretend you don't know cross multiply for a second. How could you get here? And I'm just going to give you a hint here. You don't have to get straight to here. Like you could do whatever you want. Like you want to find like another, I don't know. I'm just out of curiosity. Like if I was to say,
I think we can say like if we say like number 1 is 18, so each number is like increasing by 18.
Super
So
cool.
Yeah, like for box 5, we have 90. So if we add other 18, so it's gonna be how much? 18, 100, 100.
Oh, this is the rise and run thing, isn't it?
Oh, interesting. Someone's
It's going-
someone's cutting to the chase here.
Okay,
Wow.
so it's going up by, so for each box that you buy, the amount of flowers go up by a certain amount.
Absolutely. Absolutely, it does. I love that some people with their cameras on, they're like mouthing to to everyone. They're like, this, yeah, I got this. This is great. I love it. Here's the question I have for you for a second. I'm curious. Okay, I'm going to ask you a question that I didn't ask, but I'm curious if I could get to 10 boxes. First off, can I get to 10 boxes? And could that be helpful with getting me closer to 101 boxes? So first off, is anyone able to help me? You can just throw it in the chat if you've got an idea, like what would you do to get to 10? And I'm going to argue there's more than one way. Oh, some people are saying double 90. Go ahead, whoever has the mic on. Is it Marina?
Yeah, but can you multiply 101 by 18?
Whoa. I just heard an idea to go like take 101 and multiply by 18. And I'm going to leave that there because I don't know what that is personally, but maybe you do, and that's cool. I'm going to say, I'm curious to see if you're right. And maybe you feel like you're right, and I'm curious. Without a calculator, I should have told everybody this. Without a calculator. So some people, I want to say, some people said they doubled 90 and they got 180 for 10 boxes. So they went like, basically they're like 90. If I double that, I get 180. If I double 5, I get 10. I'm curious, can that help me get closer to 101? And by the way, in my table, I don't have to be in order like on this tape diagram. Like I could do whatever I want. So I could go from like 10 and 180 to like 20 by doubling, or I could, I don't know, are you brave? Like, is anyone brave enough to go from like 10 all the way to like 100? Like if 10 flowers or 10 boxes gives 180 flowers, how much is 100 boxes going to give? I love it. I see more lipping and now people typing, which is fantastic. I see Courtney says 1,800. If you feel good about 1,800 flowers here, I want you in the chat to just type anything. It could just be like a mash of the keyboard. Just be like that. Oh, people, you're also proper. They're saying yes or yas, and I just said mash the keyboard. So good for you. Like you're much more, you know, I guess formal than I am. I love it. Fantastic. Now I'm curious, who can articulate why that's true though? How do I know that's true? And then how do I get to 101? Because I'm at 100, that's good. I'm feeling good, but now where do I go? What do I do?
So you just add 18 to the 1,800.
Oh my gosh. Holy smokes. And I'm even going to like rewrite this. It just, to me, I hate putting it out of order. So it sounds like I've got one more box. So I'm going to add one. And you were saying like, you know, one box is 18. It's like you got like a whole cheat sheet behind here. It's amazing. And you're going to add 18 over here. I got 18. Is that fair? I didn't even set it up that way. I just kind of made this up on the fly. So that's pretty cool. I feel pretty good about that. I'm curious if I do this in the calculator, just to double check, someone who it seems like they've got like, I'm going to call it like a trick, like an algorithm that's going to work here. It's interesting. They said like, you just take 101 and multiply by 18. Oh my gosh, look at that. I could just replace that. That's super cool. I like that a lot. Okay. So 18. The only difference with this one though, is to use the strat. Oh my gosh. You know what I just realized? Remember our strategy earlier in the day that we used where we broke this number down? Holy smokes. I think I could use that over here. Look at, I could go like 100 plus 1 times 18 And I'm like, well, 100 is 1800. And then 1 times 18 is 18. Oh, I feel pretty good. Oh my gosh, like I've got like a lot of ways to do this. Now, does cross multiplying work? I want to uncover this because some of you are going to be like, I don't care what he says, I'm cross multiplying. That's just the way I'm going to do it. And that's cool. So let's see what happens when we cross multiply. So I cross multiply, I'm like x times 1. Some people are like, I don't know what that is. So it's just x, that's good. And then you have 18 times 101. Oh my gosh, look, that's what we have here. And I want to go to the chart here for a second. I have 18, like, so basically what you did is you took this number divided by that number, and then you multiplied the result by 101. And that is why cross multiplying works. But I'm going to just pause for a second and say, like, imagine if you were doing this work in the table all through your schooling, and then you came up with this rule because you knew it was a trick that works. I want to like reframe this for a second. Like, look at this. This is 1 over 18 equals 101 over x. I'm going to just flip this. Look at 18 divided by 1 is equal to x over 101. When I do cross multiplying here, it's still going to give me the same result, but I want to clarify something for a second. What I want to know is this. And basically what we're saying is, remember, all of these ratios in the table are equivalent. You remember when we said that earlier? They're all equivalent. So 1 over 18 is equal to 2 over 36. It's equal to 4 over 72. But the inverse is true as well. 18 over 1, there it is equal to this number divided by 101. This is the rate. This is the rate. We just don't know part of the rate. So we're just trying to isolate what is part of this equivalent fraction, and we can see it in this table. There's so many ways that we can solve these problems through a table that don't require us to possibly maybe make a mistake or forget a step when we're using cross multiply. So you can use cross multiply. It's not something I typically teach just simply because it's very easy to forget. And it's also very easy to mess up because, you know, you get into other scenarios like if you add a 4 over here, then all of a sudden it breaks down and people don't know why. So that's why I sort of move away. But I want to get back to something someone said in the room. Someone said, isn't it this RAS over run thing or this slope thing or this crazy thing? And the answer is yes, it's hidden in here. It is here. It's intuitively here. And there's a few things that I just want to highlight. So first off, what we have over here when our friend shared this is that you actually had, if we call this X and we call this Y, okay, X boxes and Y flowers, okay? It's really just a ratio of X to Y. And what we actually have, like if I wanted to find anything in this row, basically I could say, okay, well, Y is equal to, my number of flowers is equal to 1 box times 18 flowers, or 2 boxes, or 3 boxes, or X boxes. And really what we have here is our equation, and here is our rate of change, like we saw earlier from our original division. Remember, this divided by that is 18. This divided by that is 18. This divided by that is 18. This divided by this will break your computer. 0 divided by 0. So be careful. But any of these we can divide and we are in good shape. Holy macaroni. That is pretty impressive. So this is our graph, and our graph would be boxes and flowers. And for each box we go up, 18 flowers. What is that, 36? And then what are we at, 50? Where's my rate? What am I doing? 54?
Yeah.
And we have, I want you to picture this for a second. It's like, okay, I have 0 boxes, 0 flowers. 1 box, 18 flowers. 2 boxes, 36 flowers. 3 boxes, and we've got this beautiful linear relationship. But it's actually like, it's like a special kind. And the reason it's a special kind is because it starts at 0 and it rises by that same rate of change. Okay, so it is a type of linear relation. And if you want to reveal that rate in a proportional relationship, you just have to divide across the table and you're good to go. Now I'm going to pause there. I'm going to take a breath and I'm going to sip my water, and I'm curious, how are we feeling? I see Casey has a question. Couldn't you also do 18 times 101 and then divide by 1, or is that just for proportional? And I'm going to say, yes, Casey, you could do that. And you could divide by the 1, and keeping in mind, just when you divide by 1, nothing's going to happen. This is a direct, I love that someone mentioned that. The new grade 9 curriculum was just released, the de-streamed grade 9 curriculum, and they took out the 2 types of variation, the direct and the partial variation. They removed that language from the curriculum. So I don't know if the test will also remove that language to suit. Holy smokes, mind-blowing, I know. Now, I want to let you know about a non-direct, okay? And it's probably worth that we talk about this a little bit, because really the only thing that changed, like right now we have a proportional relationship. You'll notice these are all ratios. I can write them all as ratios. There's like a 1 to 18. I've got a 2 to 36. All of these are ratios. When I divide the ratios, I get the rate. Now I'm going to also tell you something. When we divided these ratios and got the rate is the slope. That number is the slope. They are the same. They're the same person, because this 18, this rate, is what's causing this line to slope upward. If it was minus 18 or negative 18, it would cause this line to go downward by 18, right? So this is the slope. Slope is just more of an abstract term because it's math and we just want to make it harder on everyone, right? But really it's referencing the rate on more of a graph representation because it's actually sloping the line. So that number is what causes this line to slope. So now I want you to think about this for a second. If I change my ratio of flowers to boxes down to 9 flowers per box, 9 flowers per box. So now that would be y equals 9x. My whole table changes, 1 to 9, 2 to 18, 4 to 36, like all of that's going to change. My question to you is this: what's going to happen to this line if now my slope, my rate of change is halved? What's going to happen to this line? Who wants to give me like, kind of like describe what's going to happen? Don't have to tell me values, but like what would happen to it? Is it going to like go over here? Is it going to come down here? Is it going to like move up here, down there? Like what's going to happen? Few people are saying less steep. Or if you're thinking less steep, what are your thoughts? Do you like everyone agree? Less steep. Let's think about this for a second. I'm going to graph it in this color. Okay. Well, now it's 9 flowers per box. So 1 box, 9 flowers is like here. 2 boxes, 18 flowers. 3 boxes, 27 flowers. Oh my gosh. It's less steep. Definitely less steep. And actually, look at this. 18 flowers, we halved it. Look at, you've actually halved the distance between this line and the x-axis. Do you see that spatially? How like that's like right in the middle. Super cool. So we've modified this rate, and thus the graph will modify. The table will modify, the proportions will modify, the equation will modify. Okay, so I just wanted to give you kind of like a heads up on that. Courtney's saying, is there a rule where the lower the slope, the less the steepness of the line? And you are absolutely correct. Because if you think about this, imagine it's 1 flower per box. 1 flower per box is going to be like 1 flower, or sorry, 1 box up 1 flower. It's going to be real close to the x-axis. Like 3 boxes, 3 flowers. I'm at 10 boxes and I'm only at 30 flowers, like way over here, 30 flowers. So that's going to be a really, really, really less steep line. Now, if it's a negative value, right? Negative value, keep in mind though, if I go to negative, now the steepness of my line is just like the line's going to change like this. So as the negative value gets further from 0, it becomes an even smaller number. Like if I go to negative 100, my line's going to be super steep. It's just the opposite direction. Cool. Like 100, positive 100, negative 100. It's going to be like the same steepness, just different direction of the line. It's kind of like you're going up a big hill. If you're reading from left to right, you're going down a big hill, reading left to right. Okay, so that's the slope. Slope is really, it's actually a pretty cool dude or dudette or whatever. So I'm curious here. I want to play with something. We're doing a lot in like one session, so I apologize for those who are like, what the heck? How many people have heard of rise over run? Okay, so I'm kind of approaching this. I would never teach my class like, hey, who's heard of rise? Like we would actually explore it for many days and then, oh yes, lots of people. Rise over run, rise over run, rise over run. What we did when we graphed was we used rise over run. You didn't really realize, maybe some of you did, some of you didn't. But when we're graphing a line, what you're doing is you're actually using rise over run. So like when I go over here, here is my run. And here is my rise. Okay. Now, the rate is what tells me how much I'm rising and how much I'm running. Like rise over run is basically saying, go back to what you know in this table. And I want you to tell me, like, in this case, it's like, I want to know how many flowers should I go up by and how many boxes should I run by?
Go across.
So if I think about this, I could do this a number of ways. Would you agree I could rise by 18 flowers and run by 1 box? Would you agree that's how we do that? Let's check it out. Rise to 18, run 1 box. Oh, look, I'm on the line. Wait a second, wait a second. How about if there was 72 flowers? Keep in mind, we have all the other information, so seek out the information. You don't have to calculate anything here. 72 flowers, how many boxes is that again? In the chat, anyone? Aha, math. I love that your name's math. It's fantastic. Yes, 4 boxes. Okay, let's double check. Let's see if rise over run works. Rise over run, rise over run. Okay, I'm going to start on the line. Oh, start on the line. I'm going to go up by 72. Oh, shoot, I didn't do 72. There's 72. There's all the way to 72. And I'm going to run 4 boxes. Oh, shoot, I don't have 4 boxes. Here we go. 1, 2, 3, 4. Oh my gosh, look at that. It brought me right back to the line. Rise over run is just the ratio with a weird word. And it's used specifically for the graph. But basically it was like, use this to help you get to the line. And the cool part is I can be on the line anywhere on the line and get back to the line using rise over run. Are you ready for this? I'm going to look at the table. Here's rise, here's run, rise, run. 36, I could go up by 36. That brings me to 72. Okay, I'm up 36. and I'm gonna run 2. There's 1 box, there's 2 boxes. Oh my gosh, I'm back on the line. Rise, overrun, boom, I'm good to go. All it is the ratios. Now, the only other thing that you need to think about is the scenario when I say, you know what? Something a little different is happening here, because I'm going to tell you this. I'm going to say that actually I had 72 flowers and I divided them into 4 boxes, but there were already 3 flowers. I'm going to make it easy. Let's go with 2 flowers on the table. So I want you to think about this for a second. 72 flowers in 4 boxes. And we have 2 flowers, and I'm going to say like for the bride and groom. These are basically for, I don't know, I didn't think through that context very well. But we have this extra 2 flowers, and I'm going to ask you for a second, like what's going to change here? And I'm going to leave our table, our original table here. I'm going to throw a new table down. I'm going to put boxes, and I'm going to put flowers. And I got to ask you something. We had 72 flowers in 4 boxes. We know that that was 18 flowers per box. My question to you is, how does that impact this table now that we have these 2 additional flowers that are just like not in a box, they're just to the side, they're just hanging out? How's that going to change my total number of flowers? And I'm going to tell you this, that every box has to have 18 flowers in them. So 4 boxes is 72, 5 boxes is 90. But the problem is we already have these 2 that we need to count. What's going to happen when, well, let's start at 4 boxes. How many flowers are we going to have if we know that this box, 4 boxes has 72, but we already have 2 on the table? How many flowers are we going to have here? I think I saw, and I'm trying to see whose, I can't see whose name the video belongs to, but I saw someone go like 74. And would you agree that if I have like 2 additional flowers on the table, it's going to up it by 2, right? Makes sense. How about when I go back to like 2 boxes? 2 boxes, 18 in each box, and then 2 more. What's that going to be? That's going to be 36 plus 2, which would be 38. Yeah. So 2 more. It's like we're going, okay, plus 2, plus 2, plus 2. Wait a second. Plus 2. Shoot. When I have no boxes, I have 2 flowers. When I have 1 box, I have 20 flowers. Yikes. Things get a little bit hairier here, but not that hairy. Okay. I want to go back down to my graph over here. Let's start with the graph. Here's our boxes. Here's our flowers. Okay, I've got, 1 box, 2 boxes, 3 boxes, 4 boxes. I'm even going to, over here we've got, oh yeah, this one's a little more challenging, because remember, we have 2 flowers. And then now we have like a little more, like a little higher than 18. And then we're a little higher than 36. What happened to our line in this scenario? What happened to it? It might be hard to see. I'm going to zoom in for you. Like, what happened to our line now that we have this like plus 2-ness going on? Here's our original line, this pink one. Whoops. Original line, new line. What's going on? y starts at 2. It doesn't start at 0 anymore. So know what ends up happening? What ends up happening is, even though there's a rate that exists, it's
At 0.
it's buried, right? It's buried here because it's like, what I've done is I've taken this entire table and I've shifted the whole relationship. I've shifted the line up by 2. I've shifted every number in this table up by 2. So the whole thing is shifted. It's almost like it kind of like we took these numbers and we went 1, 2, and like shifted it down. Or I guess you could look at it the other way, right? Like shifting the 0 this way. It's like, oh my gosh, like we've shifted it. And when we shift it, this is no longer, this is not proportional. But it is still linear. It is a linear relationship, but it is a partial variation. My question to you is, what's going to change then about the equation? Here's the original equation. I had 18 per box, and that's it. But now I got 18 per box, but I had 2 on the table already. What's going to happen? What do you think? 18 per box. Yeah, it is not proportional. So right here, yeah, you are right. It is not proportional. Okay, this one is proportional. It starts at 0, goes up, and you can kind of clearly see the rate in the table. Here, the rate is kind of buried a little bit. So basically what we've got to do is we've got to highlight that. Now my equation is not, it's not just going to be y equals 18x. It's going to be y equals 18x plus 2.
Yeah.
So that plus 2 just kind of introduces itself. A lot of people see this as y equals mx plus b, where this is the rate or the slope. And this is what we call the initial value, or the y-intercept. So we're starting at 2, not at 0. And that's going to bump my line up. So what I guess I'm saying is, it's like when I look at this and I go, well, wait a second, there's a rate buried in here. How am I going to find the rate? Well, I can do a number of things. I could use my rise over run to figure this out. But like, what is the rise over the run if I can't see the rate? Let me think about this for a second. How would I do this? Shoot. Anybody have any ideas on how I can do that? How could I like reveal it? Some friends are saying it's 18. Jazz says the slope or the rate of change is y2 minus y1 equals x2, or over x2 minus x1. And you're right. These are all coordinates on the graph. Like there's an x and there's a y. I could take any of these, but what I want to really reveal to you is this. Like, look at this. It's like if I do the difference of these two values, like think of the difference. It's like, wait a second, 38 minus 74 is equal to 36. When I go over here and I go, well, what's the difference over here? Well, it's 2. 36 divided by 2 is equal to, oh gosh, there's my 18 again. So I can find my 18 by essentially figuring out what does it go up by each time. Here it's 18 and here it's 1. Or I can use that formula, my y2 minus y1 over x2 minus x1, grab any 2 coordinates I want and do the math on the y2 minus y1 over x2 minus x1, plug it in. It'll work with any 2 points in this line. But more importantly, really all we're trying to do is we're trying to calculate, like, how far up did I go? How far over did I go? Look at that. I went up 18. I went over 1. My rate, 18 to 1, or 18 divided by 1, which is 18. And I can see it in my equation right there. Now I'm looking at the time. It is 5:28. I honestly did not expect that one example to blow up into this, but it did. And I'm okay with it. I don't know if you are, but I'm okay with it. And I think we're gonna wrap it up there, because I do want to be respectful of all your time. And I just want to thank OTF again for inviting me to come and, you know, contribute to this conversation. I know that that friends are putting a lot of time and effort into it. Just remember, my friends, the mathematics you learned in school does not define you. You are all able to do mathematics. We just have to maybe approach it from a slightly different way. So if there's anything I can do to help, definitely let me know. As we heard earlier, that, you know, from Jeff, both John Orr and myself, we do a lot of work through makemathmoments.com. We have a podcast and lots of resources out there. So feel free. We are always happy to help. So thanks so much.